If you step into any modern hospital, you immediately see how deeply we rely on plastic. Every IV bag, syringe, and sterile surgical wrapper requires a material that is perfectly clean, cheap, and completely immune to moisture. Plastic conquered our economy because it offers physical properties that organic materials simply lack. It can be melted into any shape, it costs pennies to manufacture, and it is virtually impossible to destroy. But that exact durability is creating a massive permanent backlog. Because it never rots or rusts, nearly every piece of plastic ever discarded is currently sitting in a landfill or an ocean, where it will outlast us by centuries. Instead of disappearing, weathering breaks it down into microscopic fragments. We are now finding these tiny plastic shards accumulating in human lungs, arteries, and bloodstreams. We cannot simply ban it. Removing plastic would instantly collapse modern medicine and global food distribution. The only way out is to find a perfect, identical replacement. The bioplastics industry has spent decades trying to build that replacement, and almost every attempt hits the exact same structural wall. The bioplastic trilemma means green alternatives must be strong, degradable, and cheap to mass produce. PLA, the most common corn-based bioplastic, fails this. It only degrades in a specialized 58 degrees Celsius industrial composter. In dirt, it sits for years, and under physical pressure, it shatters. Even worse, making PLA requires massive amounts of fermented cornstarch. Scaling that up forces us to use highly valuable agricultural land to grow packaging instead of human food. Looking at another option, PHA, we see a different failure point. This material degrades naturally and holds up physically, but because it requires a complex bacterial fermentation process, it costs 5 times as much as regular plastic. These failures stem from a deep chemical limitation. Until now, scientists did not know how to reshape a plant's microscopic building blocks without mixing in toxic, oil-based chemical glues. That chemistry problem is exactly what a team of researchers at Northeast Forestry University in Harbin, China, decided to target, and they focused their attention on bamboo. Bamboo holds its shape using a molecule called cellulose. On a microscopic level, this cellulose is locked into place by intensely tight hydrogen bonds. Those bonds are why a bamboo stalk snaps rather than bending when you apply extreme pressure to it. Previous researchers tried to bypass this rigidity by taking a shortcut. They would grind the bamboo into fine fibers and mix it with traditional plastic adhesives. The result was a half-plant, half-oil hybrid that still failed to biodegrade. The Harbin team took a completely different approach. Step 1 uses zinc chloride and formic acid to safely untie the rigid hydrogen bonds without breaking the cellulose strands. Step 2 introduces ethanol, prompting the loose strands to reconnect into a dense geometric lattice, stronger than the original plant. They named the result Bioplastic. By rebuilding the plant at the molecular level, they created a material that looks and acts like standard plastic, entirely free of any petroleum-based glue. This chart compares the exact pulling force limits of different materials. Bioplastic handles up to 110 megapascals of force. That is roughly double the capacity of corn-based PLA, and comfortably beats the high-impact polystyrene used in heavily stressed consumer products. Under thermal testing, it holds its exact shape at temperatures above 180 degrees Celsius. And when subjected to heavy kinetic impact, it absorbs the energy rather than warping or shattering under the pressure. But the critical metric is what happens when you throw it away. If you drop a piece of Bioplastic into plain, unheated dirt, it fully dissolves back into the soil in about 50 days. It also solves a major problem with waste recovery. When standard plastic goes through a recycling facility, its chemical structure degrades. Bioplastic can be recycled repeatedly while retaining 90% of its original structural strength. By combining industrial durability with rapid natural decomposition and high-efficiency recycling, this bamboo molecular structure successfully bypasses the limits that held back previous alternatives. Finding a lab solution is only the first step. If a new material forces global industries to spend billions replacing their machinery, companies will simply refuse to adopt it. Bioplastic sidesteps that massive capital cost entirely. It feeds directly into standard injection molding machines without any retooling. Even better, it processes at room temperature, eliminating the need for the high-energy kilns that standard plastics require. The raw material supply is already scaled for global production. Bamboo grows up to 1 meter a day, thrives on non-agricultural land, and regrows directly from its own root system after being cut. You do not have to clear new fields or plant new seeds. Right now, researchers estimate Bioplastic costs about $2,300 per ton to produce. That is roughly double the current price of standard petroleum plastic, though that gap will naturally narrow as production facilities scale up. And that $1,200 petroleum price tag is artificially low. With global treaties tightening and massive pollution cleanup fines looming on the horizon, the true economic cost of sticking with oil-based plastic is rapidly increasing. We spent a century optimizing a material that is actively building up in our bodies and our ecosystems. Now we finally have an exact, high-performance replacement that does not force us to compromise.